In this video, I'm going to discuss this idea of the hard and soft acids and bases, which you'll often see abbreviated as HSAB. And so our acids we can categorize, and I'll talk a little bit here in a minute, well, quite a bit in a minute about how we determine sort of the hardness and softness of an acid. But we see here in this part of the periodic table how we can sort of categorize the hard, intermediate, and soft acids. So these ones in orange here and over here are the hard acids. Then these ones in blue are the soft acids. Then we can look at the hard and soft bases as well, where we see that these ones in orange are the hard bases. Then these ones here in blue are the soft bases. So the factors affecting the softness and hardness of the bases and acids are the polarizability and d orbital highest occupied molecular orbital. So the polarizability has to do with the ability of nearby species to induce polarity in the atom or molecule. And so we can see here I have iodine and fluorine, where iodine is a soft base and fluorine is a hard base, where if we put sort of a positive charge next to them, we see that the iodine is this much larger atom, and so it has this ability to sort of polarize a bit more. So we can end up with this partial negative on the side facing the positive charge and partial positive on the side facing away, where fluorine, because it's much smaller, there isn't as much ability for this charge separation to happen. So where the electrons orbiting the nucleus here would sort of get pulled towards this positive charge a little bit. But since this is much smaller, there isn't as much, I guess you could think about it as room here for the electrons to sort of get pulled over to the side. Or another way you could think about it is because this negative and this positive inside the fluorine are sort of so much closer together, those will sort of counteract the positive charge outside of it, where this negative charge inside is going to be attracted to the positive charge inside, where with the soft base you can kind of think about it that way too, where because we have this larger atom, the negative charge inside can get pulled further away from the sort of positive charge inside, and so these aren't going to be as attracted to each other as strongly as it would be in the fluorine, and so you can get this greater polarizability. And so in general, soft acids and bases are larger, and hard acids and bases are smaller. Though this is kind of a general trend, because we can look up here and see that we know from general chemistry that atomic radii get smaller as you go left to right. But what we see is that these on the left over here, even though these would be larger, are hard acids. And of course, that has to do, as we'll see a little bit, with sort of the highest occupied molecular orbitals. But we see as we kind of go from top to bottom, as atomic radius gets larger going from top to bottom, that we do get softer here. And so that's where that trend is kind of visible there. And same here, where as we go from top to bottom, it gets softer. And so as atomic radius from top to bottom gets larger, the bases get softer. But like I said, we also have this idea that the d orbital, highest occupied molecular orbital, means that the cations with large charge tend to be harder. And so we see up here, like these things with the greater charge will end up being harder than stuff that will have smaller charge. So the transition metals further right, which have their D shells filled, will be softer. And so we know that as we sort of move from left to right here, we're sort of filling those D orbitals. And so having those D orbitals in the highest occupied molecular orbital over here gives us the harder acids there. And so the idea behind this sort of hard and soft acid and base thing to is just to, I guess, come up with this, which I'll even put here in bold. So soft things want to bind with soft, and hard things want to bind with hard, and a species containing hard and soft will dissociate more readily than hard, hard, and hard, soft. And so I'll actually put these two things in bold because that's kind of the whole reason why we come up with this hard and soft acids and base thing here is because of what we have right here. This is kind of the you know the predictive power of this soft and hard acid and base here. And so we can see that this kind of helps explain the pKa values of acid halides, where hydrogen is a hard acid, which it's very small. So you can see up here this is a hard acid, and it will be positively charged, so it will not have that filled highest occupied molecular orbital. Then we have the base hardnesses decreasing. So the F minus is a very hard base, where the I minus is a very soft base, which is kind of what we saw in this example up here. And so we see that this hard interaction here has this high pKa, so it's not as strong of an acid, whereas then we go down to this HI here, where we have this soft base here, and then the hard acid hydrogen. That is a very unfavorable interaction. So we get this much stronger acid, this much lower pKa. And so we can actually see that if we go one over to the left on the periodic table, so looking at oxygen, sulfur, and selenium here. So if we are looking at these as our bases now, we see kind of the same trend where with H2O, these hydrogens or this oxygen is going to be sort of a much weaker acid here, this H2O, whereas as we go down the periodic table, we see that the acids get stronger and stronger because this hydrogen, again, is a hard acid, and then this oxygen is sort of a hard base. And so that is going to interact more strongly. Whereas we go down here, we have the hard acid hydrogen and the soft base here. And so that will be, these hydrogens will dissociate much more readily. So that is much more acidic. So if we also consider the dissociation of the soft Lewis acid silver with the Lewis base halides, which again have decreasing hardness. So the fluoride is a very hard base, and the iodide is a very soft base. We see that the soft Lewis acid silver with the hard base fluoride here is going to dissociate fairly readily. So we're at 10 to the 2 here for our equilibrium constant. Then we go down to 10 to the negative 10 here for silver with chloride, then 10 to the negative 13, then 10 to the negative 17. So this is a very unfavorable, this is a very low equilibrium constant here. And so that is not going to dissociate very readily because we have this soft acid silver and this soft base iodide here, which are going to stay bound to each other fairly strongly. So then if we look at the hard Lewis acid lithium compared to the soft Lewis acid silver, and then looking at the hard Lewis base fluoride and soft Lewis base iodide, so we're looking at the different combinations of that. So we have our soft acid and soft base here, and so that is very insoluble. So you can only dissolve about 3 or 0.00003 grams of it in a liter of water at 20 degrees Celsius. Then we have the hard acid and hard base here, the hard acid lithium, hard base fluoride. This is mostly insoluble, so you can dissolve about 1.34 grams into a liter of water at 25 degrees Celsius. But then we have the soft acid with hard base and then hard acid with soft base here. And so we see that those are quite soluble. So 1791 grams per liter and 1670 grams per liter, both at 25 degrees Celsius. And so that's, looking at kind of that predictive power of this soft acid and soft base, and then the hard acid, hard base being much more strongly associating than a soft hard or hard soft. And so we can also look at how this can actually predict something that is observed, even though we have the sort of strong Lewis acid zinc. And so this, when I say strong here, I'm talking about something that I will discuss more in the next video, which is sort of looking at like hydrogen ion affinity in the gas phase, which is a much more sort of thermodynamic thing, which I'll discuss in the next video. But for now, we'll just know that using those methods, zinc is considered a strong Lewis acid, and this oxide is a strong Lewis base, which you would then predict that they should remain bound to each other if we don't take these hard soft arguments into account. But since the zinc is a soft acid and the oxide is a hard base, we can actually see that when we react that with this hard acid lithium and this soft base butane here, that we actually see that this is favorable. So this zinc, this soft interaction of the soft Lewis acid zinc and the soft Lewis base butane here, this is actually more favorable than what you would predict from just taking the strong Lewis acid zinc and strong Lewis base oxygen here. But since this one is soft, since the zinc is a soft acid and the oxide is a hard base, we can actually predict that this is going to be more favorable. The products here will be more favorable than the reactants. So that is sort of one of the sort of strengths of the predictive power of this soft and hard acid base chemistry here. And so it also predicts something that is observed when you actually observe these using different spectroscopic methods. So we see this was called bonding isomerism of thiocyanate, which is sulfur, carbon, and nitrogen bound to each other with Lewis acids, where the softer sulfur, which is a larger atom than the nitrogen, is going to bind with softer Lewis acids such as mercury. So this will bind with sort of the sulfur pointing at the Lewis acid here, whereas the harder base nitrogen will bind with the harder Lewis acid such as zinc up here. So we said zinc was soft up here, but compared to this mercury, it is a bit harder. And so again, this hard and soft thing can be a little bit relative at times, but there are quantitative methods for thinking about this as well. So there is this notion of hardness and softness can be put in quantitative terms, where we have this eta equals I minus A over 2, and this chi equals I plus A over 2, where I is the ionization energy and A is the electron affinity, both in electron volts. So the eta is called the absolute hardness, and chi is called the absolute electronegativity. And so we can think of ionization energy as being how tightly bound the highest occupied molecular orbital is. And the electron affinity is the measure of the lowest unoccupied molecular orbital energy. And that means that our eta here is measuring half the distance between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, where chi is sort of the midpoint between the two. And so we can look at this, which is just a picture that I took from my inorganic chemistry textbook, which is the Meisler and Tarr third edition. And so this is looking at fluorine, chlorine, bromine, and iodine. And so we see that they have very similar lowest unoccupied molecular orbitals, but then they have these fairly different highest occupied molecular orbitals. And so the fluorine has this very large difference between them, and then this low energy midpoint between them. And so that is telling us that this is a hard base here, because if we look at the sort of magnitude of this, then we would say that this chi is larger than the chi on, say, the chlorine here. It's lower in energy, but it's a higher magnitude, and so this can be used as kind of a quantitative measure of the hardness and softness of these Lewis acids and Lewis bases. But there is also this other quantitative method. So it's this Drago-Wayland quantitative system, which uses these experimentally determined energies. So if we are reacting this acid and base to form this acid-base adduct here, we have this minus change in enthalpy equaling this E, which is sort of the capacity for ionic interactions. So the capacity of the acid and base multiplied by each other, plus the tendency to form covalent bonds multiplied by each other. And those are in units of kilocalories per mole. And so we have our I2 as the reference, and then this NN dimethylacetamide and diethyl sulfides as the reference bases. So again, the magnitude of this change in enthalpy is a more favorable reaction. And so we can consider these reactions here. So we have this diethyl ether, this diethyl sulfide reacting with iodine. So this is the diethyl ether here plus iodine forming this adduct here. And so when we calculate what we grab from this table here for our Ca, Ea, Cb, and Eb here. So we have our diethyl sulfide here for the Cb being this 7.4, and then this point 0.963. So that's for our diethyl ether here, then the 3.25. So we have this Ea from our iodine times this Eb from our diethyl ether, plus this Ca from our iodine times this Cb for our diethyl ether. And we see that gives us minus 4.21 kilocalories per mole. Then we do the same thing. So this is very similar to the diethyl ether, except we exchange this oxygen for sulfur. So the oxygen, remember, is sort of the harder the harder base here, and the sulfur is the softer base. And so this method here sort of bears that out as well, where when we calculate this delta H for the diethyl sulfide here, we get minus 7.74 kilocalories per mole. So this has a greater magnitude than this, which tells us that this is a more favorable reaction than this one. And so we have this this softer base here forming an adduct with this soft iodine here, with this soft acid iodine here, and so that is going to be more favorable than the diethyl ether with the iodine right there. And so and both of these methods, this sort of soft, hard, and this Drago-Whelan quantitative system. So what you find when you actually dig down into it is there's a lot of different exceptions to the rules and all this kind of stuff. And so these are, they're helpful tools, but they're not like real hard and fast rules about things. Like I said, you'll find a lot of exceptions to some of these rules when you actually dig down into it. But this is just kind of an introduction to this idea of hard and soft acid and base theory, which is a way of sort of thinking about the relative strengths and weaknesses of different acids and bases. And I will talk about other ways of sort of thinking about this in the next video, where we actually look at sort of the, I guess you could call it like the intrinsic strength of acids and bases. So it's called like proton affinity, which is something that's usually measured like in the gas phase for these. And so this is a very thermodynamic kind of thing. But anyway, I don't want to get too ahead of myself. This video was the hard and soft acid base theory for thinking about the relative strengths and acids of bases. But anyway, I hope you found this video helpful, and I will see you in the next one.